Okay, welcome everyone. And thanks, Anirudh, for pointing this paper out. It's a little bit, I'm sure, as you've noticed, like kind of underwhelming given that dynamical systems is such a powerful tool, and even just playing with nonlinear dynamical systems gives you so much interesting stuff that is sort of suggestive for things happening in the brain. And they sort of point in the general direction of dynamical systems and throw away all the nonlinear terms, which for me is hilarious. But I understand why they do it. But let me just sort of go through. Anyway, just if anyone has impressions or wants to summarize anything, just jump in. Well, I've underlined some bits that I can talk about. Yeah, so I like this very first statement right in the third paragraph here about this approach, dynamical systems, has helped us to understand cortical responses that are dominated by intrinsic neural dynamics as opposed to sensory input dynamics. This is a sort of revealing, sort of sociologically revealing sentence, right? Because what everything has to be dominated by its internal dynamics in the sense of its own structure. So what do they mean really? I think what they're gesturing at is the idea that a lot of people who come at the brain, as I said, in this kind of symbolic way, discretize everything. They discretize the space, they discretize time, and you have these units that are just sort of doing computations. And you typically understand them in terms of some fairly simple operation and input. So everything that the neuron does is, or the region even, or a column is just whatever the input demands that it does. But anyone who's recorded or looked at data will notice that the stuff that correlates with what you think the input is typically buried in all kinds of stuff that has very little to do with whatever it is you're correlating the animal with what the animal is doing. So one way to think about that is that the inputs are just sort of bumping a system that was already doing its own thing. So you could imagine a group of neurons that are, just self-exciting and inhibiting each other and producing all sorts of dynamics, and not just sitting waiting for input. So what I appreciate about even sort of this bare minimum version of dynamical systems in neuroscience is that they point this out, that these parts of the brain are just sitting around waiting for input, and you probably won't be able to understand them if all you're looking at is input dynamics. But they say hilarious things like this. A prediction of this dynamical systems perspective is that dynamical features should be present in the neuronal population response. What can that possibly mean? But yeah. So then it's a decent review of basic ideas about.
I mean, everything is a rotation. That's what they mean.
Yeah. So they review stuff that we looked at in far more detail recently. They talk about pendulums and stability and all that stuff. And figure 2 is nice because for those of us who have been sort of looking at these diagrams of state spaces for more abstract systems where one of the axes is velocity. These diagrams where N1, N2, and N3 are just firing of 3 different neurons. It's more sort of intuitive to understand what the state space is. We're not talking about the velocity of the neuron or some derivative. And so movement is just movement in firing space. But what they're building up to is this idea that you can do dynamical systems analysis basically in PCA space. So I'm guessing a lot of you know what PCA is, but Kale, would you like to give just a little intro to what PCA is? I always get confused by what it is.
Sure. Well, it draws a lot on the eigenvectors and eigenvalues that we talked about before. I think my favorite example is actually using a standard data set of irises that's really common, where people, I forget who measured it first, but the measurements were of the iris petals and the iris sepals, which are like the little green parts that look like petals but are actually little leaves. And they measured the length and width of the sepals and the petals. And if you wanted to examine some underlying correlational structure that describes these measurements more simply, you could look at the correlations among all the sepals and petals and create a new eigenvector that accounts for that variability. And that first one is probably going to be something related to size, general size of the petals or the sepals together. So it'll be flower size, basically. And then depending on the kind of PCA you're doing, and the terminology gets inconsistent here, so you have to be careful. There's orthogonal PCA and not orthogonal PCA. So an orthogonal PCA, by definition, the next component is going to be accounting for the variability in those petal length and sepal length that is orthogonal to the first eigenvector. And in non-orthogonal PCA, also called ICA, then you can get whichever is the most, accounts for the most variability next, regardless of orthogonality. And that's the basic idea is you take a bunch of measurements, they can be lengths, they can be questionnaires, they can be firing rates, and you account for the most variability, and then you take subsequently however many more vectors you want to account for more variability. So it's a transformation that simplifies and condenses a whole bunch of measurements into as small number of measurements as you want. I think that's the best way to explain it. And usually those components are considered latent variables, especially with ICA when they're not required to be orthogonal. They have some meaning, like size, or if you ask a bunch of questions about personality, then it would be like a single personality construct. Or if you're looking at neurons and you have to have a bunch of measurements about aspects of neurons, the underlying PCA might be a kind of firing or something like that. So that's my intro explanation.
Yeah.
So there's probably another thing worth mentioning about PCA is that the directions that, so you have a bunch of orthogonal eigenvectors in the case of orthogonal sort of PCA, and those all are in the, they're ranked by variance. So the idea is that you want to explain the most variance in the data by taking these orthogonal components. And so that's, and so you wind up with these like uncorrelated things, right? But this is what I think is one of the major like kind of pitfalls of PCA when it comes to dynamics, because you don't always expect dynamics to be uncorrelated with one another, for one. Then let's see, I mean, like even like, you know, coupled dynamics that, you know, that are in some sense, you know, that they're functionally relevant. You know, you might want or might not want to decouple them that way. But then it's also possible with dynamics, I think, I might be getting this wrong, but you can wind up with, by using the PCA components, you can wind up with like kind of result vectors that are outside of your original space, because let's say you have like a something like that is non-negative to begin with. Your PCA vectors are going to center this, and then they're going to make some negative out of it, and then you can like wind up with something that's that is outside of the original data set. Now, again, I could be wrong about this, but because I haven't thought about it in a while, but that is something that's come up in the past. So
I don't know about that issue, but I did want to comment on the ordering by variance accounted for is sometimes a nuisance in fMRI ICA, which is often done with the intrinsic networks. The order of the networks is arbitrary by the data set. I mean, it's not entirely arbitrary, it's how much variance, but for example, you might get the motor network first, in an fMRI ICA, and then the visual network, then the default network in one subject in one session, and then another session it might be default first, then visual. So it's the amount of variance is often not very meaningful, but sometimes it is. In the case of like an iris data set, if you collected it again, size would still be your first component. So it's in terms of the dimensionality reduction, it's not always consistent depending on the kind of data you're looking at.
I haven't done this stuff in a while or ever actually, but when do you z-score the data? And like, so for instance, if you have data that after you z-score it, the particular variances you have are not so different. Is that part of the reason why that might happen? That the systems aren't that variable? Or
I do know it needs to be centered, but I don't remember the details.
Yeah, so another thing I was thinking about is something that I was talking about with I think several of you, the difference between linear independence, statistical independence, and orthogonality. So Himanshu, I remember you had a good way of explaining this, like that these are concepts that sometimes get tossed around together, and particularly in neuroscience, when we're trying to understand data dimensions, perceptual dimensions, and measurement or these kinds of rotated dimensions, it's good to keep them all separate. So Himanshu, could you just like explain especially the orthogonality versus linear independence and statistical independence?
Yeah, so I usually try to think about, so the example that I like to use to talk about this is like the rolling of two dice, or a number of dice. Like if you roll a die, a set of dice, and you get some result, right? Let's say you're rolling two dice, you get 1 and 5. You can think of that as a measurement or whatever that you might like to collect. So one thing that we know that is the result of each die is generally independent of the result of the other die, right? If I roll 5 on one die, it doesn't really affect the chances of me rolling, say, a 1 on the other die. And statistical independence tries to capture that in any given data set. We're collecting two measurements. How much does one measurement affect the probability of like measuring something else on the other side in the other measurement? Linear independence, on the other hand, tries to capture it's the representation of your measurement in some sense. So let's say if I want to like represent, or if I want to capture the sum of the total sum of die of what my roll is, then to roll a 6, there are multiple ways I can roll a 6. I can get a 5 and a 1, or a 3 and a 3, and in that perspective, the sum as a measurement is not linearly independent, or the two die are not linearly independent in terms of revealing what the sum is. And so that's like where you can have cases where what you're measuring is or is statistically independent, but not linearly independent, and vice versa, depending on the scenario. And then orthogonality is much simpler. It's just like whether, like Kay was saying earlier, that your dimensions that you're using are normal to each other or not.
Yeah, so
I did want to mention one other thing, which is underappreciated a lot of the time. Principal component analysis, or PCA or ICA, are somewhat analogous to descriptive statistics as compared to factor analysis. Factor analysis incorporates an error term that PCA and ICA do not. And that error term allows for better generalizability to the population that you're recording from. Factor analysis is not done as frequently, partially because of a historical accident that it was harder to calculate. And it takes, now we have computers, and it doesn't take a computer that much longer to do a factor analysis instead of a ICA or PCA. But It depends on the size of your data.
Is-
Generally, factor analysis is preferred if you want to generalize to the population because of the error term being incorporated.
Is the error over individual components of a single eigenvector, or is it across?
It's for items. It's for items to create the component. So when you do the correlation matrix of all the items, each item, the error term for each item is carried into the factor analysis in a way that I don't understand the detailed math, so you'll have to look it up.
So all this is kind of caveat or like warnings, because what's happening in a lot of these methods is projection. And we talked about, and Fitzhugh was very careful to say, well, what we're looking at is not a dynamical system or not a phase plane. And you don't see that kind of care anymore. People will just call a projection into a smaller space a dynamical system, or they call it a phase plane. So you have to be kind of aware that we're looking at a much lower dimensional projection compared to the original data. And then people are looking subsequently for subspaces within that.
And if you look at the plots, it's the craziest one, right? What do you want for a phase plot for foot rate? You want the actual variables that you actually are modeling to be the variables as the dimension, right? X and Y and whatnot. That's not what most of these people do. It is projected onto the PC space. And it is the phase portrait on the PC space. PC space. It's like, it's not even phase portrait anymore. It's whatever data fitting that they've done, and they kind of want to put it back in that. So it's not, they're modeling on the whole PCA, but then the projection is onto some whole population response, and then they will project it back to some dimension of a PCA, rather than the actual variable that they were part of that linear system even. So it's a very bizarre.
So just to confirm what you mean by that, is it that they're first transforming, then doing their time evolution operator on the PCA space, and then confirm, and then
I'll give you the rundown for that JPCA paper because it's in vogue and all that stuff, but it's a very problematic paper for very many reasons.
Okay, yeah, that's what I was hoping for.
So here is the short version. So they recorded from motor neurons, really good quality data, while an animal is performing a sort of reach movement. So usual belief is that these neurons in the motor cortex are kind of coding for a lot of different parameters, joint angle, the traditional idea of like it's doing some sort of a sensory motor transformation, and you'll finally get that converted into joint angles and muscle position and whatnot, and the animal, the old Georgiopoulos kind of idea, and coding, I think it was a reach out task, if I remember correctly. They recorded from these, 500 neurons or so. And this is what they do. They create a population response of these 500 neurons during that task at various time intervals. They have some markers to say when the animal saw the cue, when the animal's cue changed, the condition changed, all that stuff. They can create a population response, and then they take the top J PCs of that population response, the J being whatever. In their case, I don't remember how many dimensions they saw through. And then they will take that J dimensional system. They will completely throw away whatever they think as non-linearities and assume that along the 6 dimensions, it's a linear correlation. So it's AX1 plus BX2 plus blah, 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 whatever. And that is for every time interval, they have that trajectory, so-called trajectory, because of the neuronal thing. So that is your X dot is equal to that some matrix times X, yes. That big. But here is the funny part. They are somehow going, their entire paper, and I think even in this review, their entire stress is that rotation is the more fundamental operation that these neurons are somehow performing, because they saw in the neuronal signal an oscillation which was at best 1.5 cycles. I don't know what makes them think that 1.5 cycles constitutes an oscillation and that's sufficient. And in fact, they make the case it's not even about oscillation. They make it the case that it's a rhythmic behavior. But this is very common in all of neurophysiology, not just them. I don't want to just single them out for this idea that showing one oscillation and 1.5 oscillations and then claim that it's a rhythmic behavior. It's endemic to the entire field. And it's just that they are now doing a little more sophisticated hand wringing that you kind of like think they've done something profound. So they believe that there is a sort of rhythmic behavior happening. And so they're like, they see this kind of cycle-like behavior in the overall population. And they're like, oh, this must be some kind of a rotation that's happening in the neuronal space itself. Neurons are encoding for rotation. So it's sort of like the animal is making linear movements, but the neurons are sort of having rotational movements. So you can think of it as this old world mechanical design, right? When you have like the Bernoulli linkages. So you can have like multiple linkages which are kind of moving in circles, but you might get a straight line. Or I think it's called the linkages of Bernoulli or something like that.
In case anybody doesn't know what he's talking about, I think he means conversion of one type of motion into another, like with gears and stuff like that.
So that's a very common mechanical idea, and they developed a lot of things. And if you look at mechanical engineering, they have that. So this is what they want to get at with this paper, the JPCA paper. And here is the remarkable part. Like, I don't understand like how everyone thought it was amazing. You have your dx dt is equal to some matrix times x, so your regular linear systems. They make explicit condition that that matrix A should be a skew symmetric matrix. They don't fit actual data to it. And for those who are not aware of it, if you have, we talked about, the Jacobian and all that stuff for the matrices and looked at the eigenvalues. A skew symmetric matrix will always have eigenvalues which are imaginary, always. It has no real roots. It only has imaginary roots. And we know what happens if there are imaginary roots for your linear dynamical systems. It's all going to be rotations. So it's like this remarkable trickery to finally show that they wanted rotations in their system, so they'll get rotation in their system. What else will you get? It doesn't, at this point, your trajectory of the neuronal values doesn't even matter. Whatever your X values are encoding, whatever your PC is doing, who cares? If I get a rotation skew symmetric matrix, whatever input I'm going to give is going to be a rotation. And this gets published in Nature, and it's like a big hot thing and whatnot. And it's like, it's like you can see how awful neuroscience is as a field when you actually parsing through logic versus curve fitting versus model. There is no distinction. And this is the standard work.
I was impressed with like when I saw a poster of this some years ago, and I was like, oh, this looks cool. And because people like the idea of like taking seriously what the ensemble is doing, and the fact that the entire ensemble seems to be moving in a coherent way is at least not treating it just as a bag of random neurons. But yeah, if you force the system have a rotation,
whatever desired motion you want, they put it into that linear system.
So just for the reminder is that that's all in it's what in figure 3. Basically, D, E, and F are all you can get when you have imaginary eigenvalues, and you either get a shrinking or an expansion, or they call them marginally stable, which I think is giving way too much credit to what Strogatz was calling a center, because it's not a great definition. Like, why calling a center stable is very strange, because if you provide energy to it, it'll pick a new rotation at a new frequency.
And it will continue there. It won't move.
Yeah, it won't come back.
Until you put up the system again, it will continue in that same thing.
Yeah, it's like wherever you put the system, it will pick a new oscillation. So I feel like it's very strange to call that a stable system.
Imagine your heart is beating. Imagine your heart is beating at some rate, and then suddenly there is a firecracker that goes. Okay, then your heart is going to start beating at that firecracker rate forever. And that's kind of the system that they're describing as like marginally stable.
Somebody was about to say something. Was it Julia?
Oh, I was just trying to figure out which paper we were talking about.
It's the annual reviews paper, Vyas et al. 2020.
Okay.
Computation. I sent it.
It's still. It's the computation through neural population dynamics.
Neural population dynamics, which is sort of like the background. I mean, it's like well put together as an explainer. There are a few things that I was still a little confused about.
Right? But before we jump on, do you mind if we just rewind back a tiny bit?
Yeah.
I share Kartik's confusion as to why rotations were assumed and then found, and why that was so miraculous. But I'm perhaps less cynical about the benefits of using dimensionality reduction to identify appropriate degrees of freedom in large data sets. I quite like the idea. That's what I wanted to hear your thoughts on, on that without the trickery. Yeah.
I don't disagree with the dimensionality reduction part at all. At some level, it might not capture the entire system, but it is a good starting point. So I agree with you on that. I'm just saying that once you've done all this, at least be a little more, like honest and like try to fit your parameters.
How I would put it is like give the system a chance to be something else in the sense that I mean, it's not like nonlinear fitting is impossible. Like you can do it. It's like the math is a little harder. So if you show that the system could be an attractor or a stable system, then at least you're saying something. Maybe it's hard to test from the electrophys perspective, but you can make some hypotheses saying that, ooh, this particular type of quasi-stable system or something like a limit cycle is consistent with the data. That would be pretty exciting, because I think I'll go further than Karthik and say that the dimensionality reduction is crucial, because for the purposes of stable behavior, you have to have invariant subspaces. So there's no doubt that the brain is doing, like what the brain itself is doing is something like that.
In fact, if you look at most data, right, like including their data, if you look at, when I say their data, I'm talking about the Vyas paper's main impetus at the level of talking about dynamics of motor control and all that stuff, is this, when did it come out? In 2012, 13, the Churchland, Cunningham, Shenoy, I don't remember all the names, Mashadlin, all those people, they had a paper in Nature talking about how neural population dynamics for reaching are rotational in nature or something like that. And I can't remember the title, but if you just type JPCA method or something like that, you'll get
cited in this.
It's cited in this, right? So yeah, you'll get the access to that. You'll see that the neurons have a wide variety of behavior. Like if you just plot the firing rates of individual neurons in that original paper, you will see that there are a few classes that you can, like, even eyeballing like average response of different neurons, you will see that there are like distinct firing patterns, which itself you can kind of like subdivide as, firing one way, early firing, say people call it transient, late firing. You have these different types of neuronal firing. That itself is a good subspace to begin with. And then, as you say, you can kind of do a little more linearization or dimensionality reduction on that. And you can even like talk about it as like these three different entities as independent, but they're kind of interacting with one another. You can force sort of like a coupling constant, can still keep them linear, but you can have like transient plus late plus early or whatever, and then have coupling constants between them, fit your data with whatever you have, find out what those A, B, C, D, coefficients mean. Maybe it is a rotation, then I'm fully on board. If not, it reveals something. So
yeah, that's excellent. That's what I was hoping your answer would be, and is sort of what I was expecting. But I just wanted to make sure that you weren't taking a sort of sniff at the entire idea of dimensionality reduction, rather the idea of doing magic tricks on the back of dimensionality reduction.
Oh, that's almost impossible. Right?
I just want to try and engage with some like this idea of rotations, because during all of this dimensionality reduction, you're not reducing out time, are you? Time is still a dimension, like that's everything is moving in time. Because if you have something cyclical going on in the time dimension, even if it's only one cycle or like a partial cycle or something, that still tells you a lot about the inherent timescales of the activity taking place within that system. Like I'm mostly thinking about just like a lot of the work on like what slow oscillations are doing outside of a sleep situation. Like there's a lot of processes where very slow oscillations are involved when there's not actually time to get in like more than one, but it's still a delta or a theta. It's just one cycle of a delta or a theta. So like, I think like if you are getting a hertz out of it, like that's still like regardless of like what the other dimensions are, like if you are getting something that repeats within X time frame, like that's going to be related to all the other stuff that's going on at X hertz. So like, I feel like that's still valuable.
Typically the timescale will be determined by the movement, meaning you're not going to get a whole lot more than that timescale. So what you may be able to infer, but which requires a bit like more looking at the actual data, will be you may be able to infer one of the slower inhibitory timescales. Like if there are many timescales, the fast ones you won't see. But if there's some late inhibition bringing the system back to like where it was earlier. So if it's just one cycle or like half a cycle or something, well, let's assume it's one, forget cycle, it just goes to some state and then comes back in state space. It's like half a cycle, right? So you could think of it even like one relaxation event. So like a charge up a capacitor and then it relaxes, right? So that time scale tells you something, especially if it's not just the GABA B time scale. It tells you something about how the system resets. So I think, like, I like to think of like whenever you get something that in the Fourier space that isn't visible in the time domain, what you're really just getting is like a quasi Poisson events that have a particular inhibitory time scale.
Which is valuable to know about.
Yeah. So back to Karthik's point about like seeing things that are like kind of like, I guess you were saying like kind of like similar dynamics and like basically kind of talking about reducing dimensionality in sort of like almost like a heuristic sort of way. It seems like it would be maybe at some point we should talk about like equivalence and like the in dynamics, like phase relationships among neurons and like things like that. Those are all like kind of dynamical systems things that are worth discussing. It's eventually probably relates to the like oscillation sorts of things as well.
In fact, when you said equivalence, and part of what Karthik said reminded me of a slightly different branch, which is related, just topology, which is that with human beings, without even any training in topology, can recognize qualitatively similar, say, temporal patterns, like an up-down versus a down-up in firing is one thing, or something gradually declining or gradually going up. And you get the impression that if they're all from the same microarray, then some common mechanism, even if they're slightly displaced in time or phase, must be occurring. Or at the very least, if you group those together, we may learn something about some specific combination of input and dynamics. But I'm not sure how you would go about it. I mean, I suppose you could do some sort of classification of the shape using. So there's all this is a bit of a tangent, but there's this whole world now of topological data analysis. I have just started looking into it, but I'm curious about looking at just the qualitative shape of a pattern without too much of the actual specifics of time.
But you're talking about, these are all, I mean, these are all high dimensional data, right? They're not.
Right. Yeah, it's a big problem.
We don't have any classification beyond two manifolds. The only two manifolds have classification. Beyond that, we don't know anything. So
what I meant was something like before even doing the dimensionality reduction. If you're doing spike separation, then you could do a classification of your shapes.
Yeah.
Of the response. That's what I was thinking of. And then sort of in a sort of not quite automated way, pick the dimensions like you were saying.
Well, so one way of doing this is just to regularize the data, and what it eventually, like, I think so my go-to for like equivalences is always synchrony, right? Like, so things that are like a firing pattern that's exactly the same. Like if two cells are firing, precisely the same, then that's like the easiest possible like sort of equivalence. But you can take like you could take some neuron, you could take its Fourier transform, and you could say that like any neurons that have like similar Fourier transforms up to 3 Hertz or something like that, you can declare those equivalent. That's also an equivalence relation. So it's like I think it's actually like really underexplored the different ways that you can rigorously, in some sense, like claim that like things are equivalent. Like you can apply any function to all the cells, and if they give you this, if it gives you the same result, then those cells are equivalent. So like it's a very wide.
Yeah. Which is,
I've
very
actually-
why the classification.
I've actually been thinking about this a lot recently. How do you show that, I guess, like two, let's say, brain areas have a similar representation? Like synchrony or like a frequency of rhythms or anything aside. Like a very simple example is just you're looking at your visual world, and whenever you look at like a red object, you have some sense of synchronization, let's say, between that red object and a red representation in some neural area. So I mean, that's one sort of more extreme case of this. I'm not even sure if you would call it synchronization, but there's some kind of alignment there that, I mean, it seems just like a mapping or something. But if there's two neighboring neural areas that share representation, how would you even deduce that through like looking at neural data, I guess?
Yeah, just looking at the neural data is tricky, right? And we haven't had that, like, how is it done with V1 and V2? Just by, correlating things with the retinotopic map. The same with auditory cortex, similar with somatosensory and motor. So that's
people can build off of that, like just in terms of what people have done with V1, V2, later V areas, like V1 is retinotopic, and then V2 is like has a topology that's determined by the adjacency relationships in V1, and so you can probe that pretty closely to figure out like what all is going on in V2, like in terms of like edge detection, contours, etc. And similarly, like there's
Isn't that all just based on the like the visual input directly? Like you're not comparing, let's say, V1 to V2 directly, but rather they're separate relationships to the visual stimulus, and then their relation to each other based on that.
So is the question you're asking that if all you had were the neural data from, say, two different regions, can you make an assessment as to whether they were the result of the same stimuli?
Yeah, in a certain sense, yeah. But without the external stimulus. Well, let's say you were like omnipotent, you could, have all the information in the circuits. What would it mean for the two different areas to be representing something that's either the same or somehow matches in some way, like cooperative versus competitive or whatever? Like that's the way that I might think about it. Cooperation versus competition between the representations.
So there's the whole like binding by synchrony, and like you're talking about binding, right? Like I think that's the yeah.
Somewhat like I feel like binding wouldn't be the first sort of word I would use to describe it. And I'm also thinking like synchrony as in like rhythmic synchrony sort of aside. Let's say you have arrhythmic activity in the two areas. Yeah.
Well, synchrony and rhythmicity are two different things. So in principle, you can have an arrhythmic
sure, right,
stimulus that's very closely mirrored somewhere else. But
yeah, I mean like synchrony in the rhythms, as opposed to synchronicity of the representations might mean, or of the two different dynamics would mean that they're doing exactly the same thing. Like neuron 1 fires, then neuron 2, then neuron 3.
Think of how they use Granger causality in the ideal case, right? What do? They stationarize it. And there's not really any temporal kind of structure to it, right? So all you're really looking at is the kind of temporal cross correlation for some sort of particular temporal windows, right? And saying, even though this is delayed by a certain amount, it's a systematic delay. So that if you treat every event as its own isolated thing with no hysteresis, and that's why you have to stationarize it, then you can say, these two systems, even if they're staggered, are responding similarly to these like punctate events. So it's a little bit like, this might not be the same thing, but if you have two filters, how would you compare them? Not even brain filter, just any filter. How would you compare how similar they are? engineers, you know, impulse response, right? So you hit it with broadband noise in a small time window, and you get a whole lot of information about what the filter is capable of. So if you're not looking at what the system is, like what's present outside the system that could be represented, all you have are like temporal because and then in that case you don't have the concept of topography because there's no representation yet, right? So all you have is temporal correlation or things like Granger or analogous filter responses. As far as I can tell, I would be curious to know if there's anything else you could try. But,
I mean, I guess I feel like the general idea of synchrony that Charlie was talking about was like the idea of things being close in some kind of representational space, like within activity space, these two things are things within this distance of representation of each other count as synchronous because of the similarity. Is that sort of what you were getting at, Charlie?
So I'm kind of getting it. I mean, you're saying that they have some similarity and some representational space.
I'm just trying to come up with like a more like narrow definition of what you were talking about when you were talking about synchrony, because I feel like there was a bunch of ideas you were touching on there.
Yeah, so it's a little bit tough for me to get down because like the concept of synchrony in dynamical systems is purely the two systems share the exact same, let's say, trajectory over time, or they sort of converge to the same trajectory. That's sort of what it means to synchronize. But you can imagine two systems. I'm trying to think of an example. Like one that comes to mind is like two people dancing, and they're doing different things, yet their activities are concordant with each other, and I guess it would be it would have to be.
Gives you a lot there.
Sorry.
Like even like they've been doing multi-person neuroscience with like EEG and stuff like that, and you do get a lot out of just synchrony.
You can get synchrony through phase clock loop or phase resetting, right?
Yes,
I've worked on the disk drives. Everything in the disk drive is all done through phase clock loops. You have a clock generated someplace, and then there are multipliers which will change the clock frequencies, and so different portions of the board or circuits could be using different frequencies to work on that. But at some point, all of the phases would be reset and they will all start again together. So you get synchrony through that. And actually, you can think of the hippocampal theta as coming down and saying, stop all your gammas. I'm going to put you all into zero phase now. Come on, go again. So at the end of a word boundary, you start again. At the end of a syllable boundary, you can start again.
But this idea of like taking the idea of a similarity without the concept of representation is an interesting thought experiment. So yeah. I was thinking of like something very speculative, which is how do you well, you still need inputs, but let's say you don't know what the inputs are. Like they're just labeled and they do things to these two networks. You could have a kind of analogy system, whereas so you don't just look at how a system responds, but you look at a couple of inputs. So you say that A and B do this to system A, and A and B do, or C and D do such and such to system, to this other system, and then you compare the differences. That's the only way, but you still need something extrinsic, like an input. You might not know.
So Charlie, think of it this way. Let's reduce it to as simple a mathematical problem as possible. You have two areas. You have some activity in some area. Forget about brain, all that stuff. You have some trajectories in some space A. You have another trajectory in space B. The trajectory being the dynamics, or it's a manifold, or whatever. Unless you give me a transformational you either tell me in which space both of them reside, or you tell me the transformational function, like is it diffeomorphic or homeomorphic or whatever, like is it the same topology as this one over here? This looks like a torus, so can I deform it slowly to a torus on that side? You have to ask either that question, or you have to give me a metric, or you have to give me something like that. Otherwise you can't make arbitrary comparison without either giving any other structure to the system, either the space in which they are embedded, or the function by which you can move from one to the other. This is kind of like what Rob was kind of like hinting at, like how do you get to equivalence in some sense? This is a question about equivalence, and it has to be answered at different levels. If you want a topological answer, you can set your system one way. If you want a geometrical answer, you have to set your system another way. If you want a dynamical systems answer, you have to combine both and still do more, and you really don't know what you have to do. So, but you have to kind of have this grounding established by a relationship. Otherwise, you can't get anywhere. Either they are in the same space, in which case you can do a simple, linear kind of translations and rotations. If they are not in the same space, then you have to specify which function is possible to go from one space to the other. Without that, you can't.
When you put it that way, you can say it very simply. If it's different points or trajectories in the same space, you just use distance or the suitable version of distance, right? And if they're two different spaces, then you have to again invent a notion of equivalence, and then that will and a metric. So that's, I think, the only way you can do it. But
what about something like the one system, in a sense, ensuring or supporting the stability of the other system, as opposed to sort of almost like making the other system less stable? Like I'm thinking you have two areas that have some dynamics, and if they're in these in the synchronous dynamics, then they kind of keep each other in their corresponding let's say states or trajectories or whatever it is. But if they're in like some states that are not synchronous, then they kind of perturb each other and try to change the other one. Like I'm thinking of like maybe something that's kind of similar to two nodes in like a Hopfield network, where the two states can either be supporting each other or pushing each other away to have the other one flip state. But instead of like binary states, think of just these, maybe each of those nodes has some vector representation, and they're trying to flip the other one to a different vector representation.
in any causal interaction, you will see correlation and see temporal. Like if they have a causal interaction, it's hard to imagine them not having either correlation or something in the temporal domain that is like a synchrony or a staggered version of synchrony. So some phase relationship or correlation has to be there for any causal interaction, right? I mean, how else would you? Yeah.
There's a concept that, I mean, probably some people here know better than I do, but it's kind of a physical analogy, which is if you have a wooden beam and a pendulum on each side, they will synchronize. They will synchronize even given considerable noise in the environment. And they will also synchronize to a particular stable state, which is that one of them will always be slightly in advance of the other, but which one is in front depends on the initial conditions. And this is kind of a very broad phenomenon that, like, if you have kind of systems that can exchange energy in some sort of way as part of a cycle, and if each individual one can cycle, then they will synchronize. And I mean, it even goes further than that, like they can be pendulums of different lengths. So like they have different natural periods, they will still synchronize, within a certain, tolerance level. And
Get
so
beating and stuff like that.
yeah, and this is like related to how, you know, heartbeats are stabilized, is like it has a whole bunch of these kind of independent but kind of linked oscillations, and they keep each other in phase. But if you care about something other than just exact stability, you could also think of in a way they're kind of exchanging information. One of them gets pushed, it nudges the other one a little bit. So, their state is kind of stabilizing, but also potentially communicating.
I wanted to ask a question about that. Do people ever model the level of synchrony as the quantity on one of the axes that is in a dynamical system? For example, in the pendulums or fireflies or whatever they are that are becoming synchronized through these little local interactions, you could imagine a whole variety of initial conditions, but the trajectories are towards synchrony, right? I guess the question is, it's not it's a mass quantity. It's not an individual quantity of the individual agents. So
is that what the Kuramoto model does?
Yeah, I just shared the link to that. So that's what
There is a
Faye
model like that.
was talking about, and that's kind of like the
order parameter.
This is the what's the parameter called? I keep
The
forgetting.
order. It's called the order
The order
parameter.
parameter, yes. So the order parameter is the one that Kale is looking for. We know for some regimes of the for some regimes.
Well, I think Kale's talking about something a little bit more general than the Kuramoto case. Like, but I think that people have like lifted the terminology from the Kuramoto case, like this sort of order parameter. I mean, really, like what you would want to do is like you take all of your dynamics and you kind of like project them onto the diagonal. So like the vector, like that's all ones. That's where synchrony lives. So that you can like think about like when you're analyzing data, you can think about like kind of projecting it onto that in order to look at what's synchronous-ish.
Have you ever worked with an oscilloscope? So when you have, you put one sinusoid on the X and another on the Y, and when they're in phase and have the same frequency, it's very boring. It's just a straight line, right? But then you move one of them to be 90 degrees out of phase with the other, and then you get a circle. And then if they're different amplitudes, you get an ellipse, and then you get
Lissajous curves.
Lysis curves. This is like physics undergrad kind of stuff. So you can look at that, but order parameter is a whole universe. It's too bad Ryan isn't here because he studies that sort of thing. That's like the bread and butter of solid state physics.
So that's kind of like
you'd identify a quantity which could be scalar, a vector, or a tensor, identified at every point in some substrate, and then you can look at the dynamics of that, how that changes, like what Rob said about putting like imagine if you have a neural network or something where every point you can define a direction, and then what you can do is you can move all the vectors to the center, and then if you like you can then sum all the vectors or look at the average. And so if it was like magnetization, then the strength of that particular, or the length of the particular arrow gives you some information about the whole system. So there are versions of this for various higher dimensional.
In fact, there are versions for this for a low dimensional one, which is like everyone started with the order parameter, at least outside of condensed matter physics with Kuramoto model. It kind of answers for only partially what an order parameter is, like what Kale wants. I think Strogatz 2 years back had a paper which is called Syncing and Swarming, or Swarming and Syncing. So he kind of combined the regular Kuramoto model, which is just going around like oscillators going around in a circle, and when they'll all move in synchrony or not, and that kind of also depends on order parameter. But it's sort of like now add to that this sort of murmuration pattern to the system. So they're not only like having phase relationship, but they also have spatial relationships. So that creates another second order pattern. That's what Johan meant by like it can be a scalar, it can be a vector, it can be. So in that swarming and sinking paper, I don't know when it came out. I think it's just called swarming and sinking. I'll check it now. They actually talk about these second order vector model. So you see that if you add a little more structure to even a simple oscillations on a circle, which is kind of what the Kuromoto model is, and introduce space and like movement of particles or whatever these objects are, you suddenly see a whole different behavior that is not easy to capture with a simple scalar order. You have to have some more structure to it. So they kind of have explored it in that paper.
Yeah, because phase is a relative quantity, you generally don't want to frame a dynamical system in terms of phase. But once you have a dynamical system, you can then extract it out. Because in some cases, you'll have to use like phase is a pairwise relationship. So you can use one thing as the phase, or you can use instantaneous phase. So there's lots of different ways to do that, which are not like if you already know what the system is and what the causal forces are, there's no point in directly modeling the phase. You sort of pull that out of the system. But yeah, that topic. So this bit that they talk about in motor control on page 260 actually relates a little bit to this debate about representation and similarity. So they frame dynamical systems, computation through dynamical systems in terms of initial conditions. And they call it a hypothesis, which is again odd, but so let me just read this out. So from the CTD perspective, computation through dynamics, preparatory activity, that's like the stuff happening. So there are these tasks where the animal has to fixate and wait for a go signal and then either move their arm or move their eye with a saccade. And when there's a ready, like hang on and wait, like when the animal knows what they have to do, they just have to wait to do it. There's preparatory activity. So a kind of, we have this straw man computational thing, but it's a little bit like how David Marr thought. So it's not exactly a straw man, but basically these sort of little computational units that do little things in a highly discrete way without sort of bothering about what's happening in the rest of the system. As one way of thinking where everything is inputs. But with dynamical systems, you don't have inputs per se, you have initial conditions. So they frame that. So preparatory activity is viewed as an initial condition. It brings the population neural state to an initial value from which movement period activity evolves, governed by both the local dynamics and the inputs. So so it's like saying, it's almost like saying that you, like if you had a valley, and in their case with all these linear systems, that's all that the system can have, a valley or a spiraling valley. The input is like bringing the ball and placing it somewhere on the wall of the valley. And then the invariance is like that every time it heads towards its attractor, it's similar. So this initial condition hypothesis is an alternative to a representational hypothesis, which suggests that preparatory activity is a subthreshold version of movement period activity. So there's a lot buried in here. It's sort of like long debates have been distilled into like one sentence. But basically, if you're using a representation framework, then what a neuron does is kind of time invariant. So if I have a V1 cell that represents this particular point with respect to the retina, it always represents that. So if I have a weak activity in that neuron, then at best it's like priming or some sort of anticipation. And in the case of the motor system, because a particular neuron is always going to cause this particular action or muscle fiber to do its thing, then you just have this lookup table basically. So one way to think about representation in the kind of trivial way that it's sometimes talked about is that it's just a lookup table, and that when the system is operating doesn't matter. Whereas the dynamical approach, even in these simplistic versions, allows time to be relevant. So you can't just look at a neuron outside of the context of everything else in the network and infer what the system is doing, which is generally true, I think. There are very few parts of the brain where you can definitively tell what's happening outside the brain just by looking at one neuron.
In some broader sense, I couldn't help but feel that this is still sort of a representationalist way of thinking.
I agree with you completely. I was like, this is like baby steps away from a representation. Because again, it's a lookup table of initial conditions, right?
Yeah.
That's the impression I got. But yeah, baby steps, I guess,
Table of dynamics too.
is what people need. So 3.2, we already talked about this Churchland stuff. So let me see. There was some other interesting stuff here. Manifold structure.
But on that note, Johan, like what
Yes.
would you say is a true sort of take on the metaphor of dynamics and applying it? Like, what would that look like? Or
I find this topic odd because so that's philosophy paper in Synthes talks about a dynamical renaissance or something like that. And as is the case with philosophers, they like to just take the most extreme version of a position and put an ism on the end. And they're like, what if the brain doesn't do representing at all? And it's dynamical systems all the way down. And it's like, slow down there. There's no need to go that far. But yeah, so there's this idea that some of you may be familiar with this, but a lot of philosophers don't like the concept of representation at all, because they're interested in from the philosophy of mind perspective that there's this whole tradition of what that word representation means. And some people think that, when I look at the pen, there's only a presentation, which is, what I see, and no other representations. When I first heard this from a philosophy grad student at BU, I was stunned because I had no idea that people were using the word representation in that way, like as if it's something happening twice in the mind. But, so beware, if you ever talk to a philosopher, you could have many hours of confusion if you're not aware that this is how they use the term. But so when the anti-representationalists in philosophy say, let's use dynamical systems, what they're trying to say is that we don't need that thing, which is hard for a neuroscientist to even understand what it means. But the other more relevant to neuroscience thing is this coding metaphor, which there's this Romain Brett paper about it. So this idea that it's very much like this lookup table thing, or that features are symbols. And so if you're using the metaphor of symbol, it doesn't sit well with the metaphor of dynamical systems. Because if I'm in a dynamical system, it's highly context dependent. Any interesting dynamical system has things like hysteresis and input sensitivity. So time is really, really important. Whereas the whole thing that makes symbols useful in the first place is that they are invariant with respect to this to a large extent. So, the letter A means the letter A. It doesn't matter if you're running, jumping, doing whatever, it's still A, and so when you say it that way, you know that the brain has to use symbols. So it's just a question of, like, with say the Friston worldview, there's a way of talking which is almost like dynamical systems, but all the computations have to happen instantaneously in order for any of that Bayesian stuff to work, right? So they look like dynamical systems, but they're only dynamical systems in weight space, or in the space of priors and things like that. But the actual sort of represent values, which represent, what happened here and what happened there, or what the means, or whatever it is they propagate through Bayesian networks, have the nodes have to attain that value instantaneously in order for all this to sort of work properly. So in that situation, again, you need to stipulate that representations are stable, and that all your computation is done after the representation. So dynamical system where quickly, like let's say there's a phase sensitive cell, it just reaches its maximum firing and then stays there, and all the computation happens during that stable part, sort of like a symbol. But if you have like some sort of weird trajectory, and that movement in the state space is the computation, as opposed to these sort of neat symbol manipulations, then dynamical systems is a better framework, I think. Is that relevant to what you were saying?
I think what I wanted out of this was like, is there, since they, as they say, that they see this as an alternative hypothesis.
Yeah.
I don't see an explicit model test that I can do.
Okay,
so
like, to answer Anirudh's question, we should do this. We have Max Shine here. He has written an excellent review of this, which is very relevant to in what way dynamical systems can be applied as at least a tool, if not the way in which you view the brain itself, to actually study the activities and the behavior of brain structures. So maybe next week, maybe now it's too late, we should talk about Mac's review that came out just in November.
Recently. Yeah.
It's just a couple of months ago.
Yeah,
I'd be happy to walk people through it if you'd like. I mean,
yeah,
I think the ideas will hopefully be interesting to folks that are kind of interested in this space. There's certainly, the paper's not anywhere near as technically adept as the kind of discussions we've had so far in this meeting, but the concept was an attempt to essentially, it's like a love note towards the beauty of the brain's implementation and thinking about how would we describe that? What are the implications of that sort of really beautiful architecture? And I think if you're kind of dressing this up in contrast to something as deep and profound as, say, Friston's framework, it's starting with the implementation rather than starting with the computation, right? Friston says, if everything's free energy minimization, how could the brain do it? Whereas this is saying the brain looks like it has a set of rules governing its interactions of the different neural populations, and what might that give rise to in terms of the kinds of dynamics that could emerge, and what kind of benefits would that confer to a system or to an animal that had that kind of a brain. So it's flipping the idea on its head a little bit and starting from the implementation. And I think that the dynamical systems framework is just the natural way to describe a distributed system of independent units that coordinate with each other and constrain and influence one another's activity to alter ongoing behavior. So I'm more than happy to kind of walk people through that. I can do that at a very superficial level, or we can do that at a kind of, PowerPoint style presentation, whatever you guys think would be beneficial. I can also try to drag Eli along because, sorry, just to finish the thought. I've got two postdocs in my lab that I could not have done any of the work without, that both have backgrounds in physics and have kind of constantly sit over on my shoulder and tap me whenever I say something really stupid and make sure that I quickly undo it. And so if I can try to get at least one of them along, that might be helpful as well, because then we can maybe have a bit more of a rich dialogue between those of you who really know this stuff backwards and those of us, I'm much more of a kind of brain, a neuroscientist and a neuroimager trying to understand the benefits of dynamical systems.
I'll send out the paper. That's the plan for next week.
Awesome.
Sounds good. Sounds good to me. I
That
was
was
planning to
super
do that
great.
anyway at some point, because I like it's rare for me to read a paper where it's like, well, I could have written this. Like for a good 70% of this, I was like, yep, I'm glad somebody is saying it. So
yeah,
great. I hope to learn what the other 30 are, and we can have a good discussion.
Didn't remember, but what Max said is really exactly what I was trying to. I made a brief mention of MAR, but there was that paper by Popel and who were the others? Who was the first author? It was
Krakauer, Popel, and Gartenfarr. It was the
grumpy
Krakauer
Krakauer brother.
Yeah,
the non-complex systems Krakauer brother.
yeah. So I actually like that paper, but they resurrected MAR in a way that they had an opportunity to say something way more sophisticated, even in the space that they had allocated for this idea. But basically, they were saying that if all we're doing is looking at correlations of neural activity, then we're not going to learn that much, and let's characterize the behavior properly. But then they have this whole thing about it was a bird or something about, well, the bird needs to fly, the implementation is flapping, and the algorithm is flapping and the mechanism is wings. And when you cherry pick your example like that, it sounds completely obvious that that's the way to do research. But like when I meet people who ask how to do research, I say, like, don't do that. You could look at that as a model to then immediately falsify with your own work, which is like how I end up operating. Is that I might have some, obviously most of us here are interested in the brain, not just as a cool thing, but because of, behavior, consciousness, psychiatric disorders, all these things, right? So I do have some functional idea in my head, but it's loose enough that I'm willing to update it in the sense that I'll have some idea of what I think a brain area is doing, and I'll start reading the literature, and then I might even find some weird mechanism that I wasn't aware of, and that might change what I think the function is, or even or one of those other levels. So there's this sort of up and down movement in that hierarchy. So having too fixed a perspective on what needs to be done can really block you from like completely redesigning what the algorithm is. I have an example of that from which was weird because I was thinking about corticothalamic loops and inhibition. So quick summary of that with hand waving, but you have the cortex, you have the thalamus, which provides excitation and receives excitation from the cortex. And you have this thin layer, the TRN, which sends inhibition to the thalamus. And we don't know exactly what the pattern is, but there is a possibility that it doesn't just sort of cause inhibition back on the same thalamic neurons that excited it, which would just produce oscillations more or less. But you also have what's known as lateral inhibition. And what that can do is just imagine that I have, this is exercise in imagination, but imagine if I have these loops in parallel, just bands. And there's a thing in the middle that's almost like that thing that switches train cars. Like, so basically you're like inhibiting, so one loop gets to win, however you decide to parameterize that loop, and the others kind of get inhibited. I was thinking, oh, this is a nice mechanism for attention, but also, and Francis Crick also really liked it as a mechanism, but it may be attention and maybe pre-attention. But as soon as I saw this mechanism, I thought, well, how do I get split attention to work? Because if I want two loops to be functioning, and if I have a lateral inhibition system, what will happen in a system like this? And if I want both to be active? In many configurations, they'll kill each other off. So he'll have the worst of both worlds. You basically neither attend to the one or the other, because if you have strong excitation to both, then you can just inhibit both. And this happens, you do get this. It'll either get double inhibition or like just cycling between the two, or highly unstable behavior.
Unless you have a system from the bottom that's propagating the activity, right? So that it's not just a blip that then gets squashed out, but you've got two blips that are propagated and they continually fight for attention. But anyway.
So they can fight, or I came across this paper which didn't have a topography to it, but like this is an example of the bottom-up level kind of mechanism. So I forget the first author's name, but basically it was a slice study where they showed that if the cortex, layer 5 or 6, was active in a sustained way, the thalamus could be disinhibited from TRN input. So the cortex could kind of release the thalamus from inhibition. So even though this wasn't part of the model that I was trying to design, I was like, oh, not only does this help with my model, like it also helps with the divided attention thing, because if I have cortical priming, I can now say, well, these thalamic regions escape from inhibition. So typically, divided attention is difficult. So I'm not saying that it's going to happen all the time, but cortical learning is slow, right? So if you can stabilize, disparate parts of the cortex to disinhibit the thalamus, then you can get that divided attention without a race condition or loops fighting with each other, which is presumably how you get more complicated chunks. Right? Not presumably. I don't mean just the mechanism that I'm speculatively pointing, but something like that, which is that when you have a topography that involves mutual inhibition, you need to have a system to escape from that, to create more interesting topographies.
Johan,
So that's an example where
it's not clear to me that split attention requires like multiple active loops. Like
it may not. And in most cases it won't.
Yeah.
So you
could still have activity that's not like participating in a loop that's fairly strong, that's sort of like ready to, and the loops could be shifting back and forth, but
exactly.
But in between there sort of is strong enough activity that it sort of still is attention, but without a loop.
Right. But but what if I want STDP between those two? I may want some amount of overlap between them. So again, the point I was making was not that this is how the brain works, but it was that a mechanism, a low-level mechanism, which was not even advertised as in a functional way, changed how I thought about what the algorithm could be. And I have a Lego block in my head that I didn't really have before. I may not have to use it, but that's one way of like being wary of like being too top down in your focus about brain design, is that you might like ignore a really cool mechanistic paper because it doesn't match with whatever your most precious function is. So it's like, be open, like if you're interested in the brain and not just the mind, you should be open to both the functions and the structures and dynamics, because the dynamic could change how you think about the functions. That's my point.
Johan, I think it would be really useful to go over that particular network as a exemplar in a dynamical perspective, because in your papers you don't really make it as a dynamical system, right?
Yeah.
You make it as a network, and if you have looking at it in state space and what are the dynamics of a particular anatomical network, to make it really as concrete as possible, that would be really useful, I think, at some point, to see how it's implemented, how a simulation is implemented.
This might dovetail with what we're doing next week, because it was the same circuit that Mac talks about in his paper. I didn't do it in a state space way because it's hundreds of neurons. I suppose I could have done some. I mean, when you look at it, you'll know that it lives in a low dimensional subspace just by looking at it. That the 100 neurons would, they were all representing more or less the same thing in bands. But
Johan, Douglas and Martin have got a really nice current biology primer on sort of like a little toy model of what this kind of circuit might look like, where you've got a bunch of different neurons that are can excite their neighbors, but then they all activate an inhibitory pool that inhibits everyone. And so it's very much a toy model, right? It's not exactly what the cerebral cortex with the core thalamus and RTN loop would look like, but it's got some of the key features. And then they kind of go through and show a bunch of the really interesting computational kind of outputs, or let's say algorithmic outputs you can get from that kind of a circuit. You can get, if you can get two separate activity patterns, you can get the kind of winner take all phenomena. There's all this other fun stuff you can do. And so that could be an interesting one to sort of sit in that space. It's certainly not a state space analysis, but it has a bit of the flavor of the kinds of computations you can get out. I could pass that around.
Yeah, that sounds good. What year was it? I could also look for it right now.
I am going to try and find out.
So
they've got two different.
So
if people don't know this primer thing, I found it randomly last year when I was reading. It's like current biology, and they get people like experts in the field to do these 2 to 3 page, really kind of concise summaries of topics, and you can just cycle through, and there's like all kinds of stuff, like nice. From everything across science. But if you find the neuroscience ones, they're often really, really good. And I'll try and dig up the Douglas and Martin one. They're the ones that they have like a empirical paper talking about the kind of canonical microcircuit.
That's kind of what and all that stuff, yeah.
Exactly, and this is like a sort of a riff on that idea.
But yeah, we have to be very careful with that riff too, because they
100%.
They like to extend what they see in V1 and V2, and then they like to make that the story for the entire brain. But they're
yes,
very, very
they pretend the whole brain is V1, right?
Yeah, they all.
This is very common among people who study V1.
So, I've met them. I met Douglas once. He came to CNS, maybe no. But one of them works. Yeah, so they are very, very staunch about their worldview. They just think that's the only right. They not only do they think that the microcircuit is the right unit, it is the only right unit. So it's like it goes like in different ways.
That would be a contentious room to be in, given my opinion about microcircuits. but yeah. So
sorry, Johan, I have to leave to go pick up my kids from school. Sure. But I'll see everyone next week.
Awesome.
And
next week.
I'll
if you want to put slides
I've already
together,
roped
you can.
Eli in. I've already wrote Eli in to translate everything I say into physics, so it'll be fun.
Sounds good.
All right.
Thanks a lot.
See everyone. Bye.
What was I gonna say? Yeah, so the part of the reason that I don't do the dynamical systems analysis is because it's high dimensional. And the other reason is that it's not going to tell me anything I don't know, in the sense that I have with just like I said earlier, like sometimes a model is like a wild animal that you just sort of learn to domesticate because it has so many degrees of freedom, right? And you're like, okay, we'll wrangle it into this state space where it behaves sort of like I want it to. Because for the purpose of actual research, a model can't just do whatever, right? It has to do something that, and you're, because of the way that the culture in neuroscience works, people are not interested in like, oh, this corticothalamic loop can also do this bizarre thing. So that's a roundabout way of saying I don't need
That's really
to explore
unfortunate too.
I know it's really unfortunate, but
because like
I don't need to
what if
explore
we
the
make
whole
the
state
brain do
space.
things we didn't already know it does?
It's a tragedy, but like people are so narrowly focused on, just the data, please, thank you, and any kind of stepping outside the bounds of what people have actually seen. People are like, well, the reviewers will give you it'll just take forever to get such a thing through. To say, unless you're only interested in like, look at this model, and
I mean, that was part of the beauty of the Hodgkin-Huxley model, is that the model made predictions that had not yet been measured and it wouldn't be collected until much later. So, I mean, that is what you want it to do, right? Is to predict things that have not yet been recorded and can be tested in a future way.
Yeah, I mean, I think that's really the beauty of the dynamical systems approach to begin with, is that you have these things like bifurcations, you have like a whole array of stuff that can happen outside the boundaries of the parameters that you just happen to be using, right? So yeah, like you're able to like change the parameters and see like what the system will do.
Unfortunately, outside of 3 dimensions and codimension, fairly small number, the bifurcation story is it's unknown. Like it's a total jungle. Like for all I know, things that I have witnessed have never been witnessed before in a network. Like how am I supposed to know? Like there's no categorization system for these things.
We should check out well, at some point, check out a like symmetric bifurcation theory. It's like very interesting, like all of the network symmetries, and you basically kind of go between them with various types of bifurcations, and they all have their different, what is it? I forget what like there are constants associated with them, like how the frequencies change and like things like that. Or how the amplitudes change. Like there's like an exponent in how the amplitude changes as you vary the bifurcation parameter, and you can predict those like sometimes in a generic way without knowing much about the differential equations to begin with. This is all like the Golubinsky, this is all the Golubinsky stuff.
Golubinsky and Stewart, yeah. You can use symmetry arguments to do a lot.
I have no idea how they do it. It's it's magic.
But yeah, the pure dynamical systems approach that we saw with Fitzhugh, right, will never be seen again. Like that was like, it was the right thing at the right time with the right problem. And in biology, I really doubt that anything will just have that right level of simplicity. I may be wrong. I would love to be proven wrong about this, but like everything else is a little bit hand wavy. Like I sent out much earlier a paper by Helen Myberg about bistability to do with deep brain stimulation in depression. Now here, the variables are, activity in area 32 and activity in area 46 or something like that, or 25 and 46. So they don't even, 25 and 46 aren't even connected much. So they left out the 25. They said, well, we'll just assume the 25 does the job. And so they have a 2-dimensional model and they show a nice bifurcation, and they say that, well, this might be what's happening with these particular people, and it's cool as far as it goes. It's a very clean dynamical systems model paper. The paper is very good, but when you're reading it that this 2-dimensional thing is capturing very little. So the clean traditional dynamical systems approach, which has bifurcations and whatever, is suited to these extremely simple systems, and the brain is way over on this other side of the table. So I think of dynamical systems theory for us, right, for neuroscientists, as learning a language and having a metaphorical feeling for these things. Every once in a while, you might want to like check something maybe, but it's like, yeah, it's sort of like just a sense of what can happen, like particularly things like hysteresis and like networks that wander. Like as soon as you get into a sufficiently large dimensional space, the types of oscillatory phenomena you get are super weird. Like maybe I'll show you some of these GIFs that I've been making of these networks that I've been playing with. I was looking for them. So I just made these.
They're RNNs.
Yeah, they're RNNs.
Recreational neural networks. We should be very careful of that.
Recreational neural networks, exactly. Where did I put them? But yeah, I'll just find it one sec. The idea being that when I saw these weird oscillations, I was thinking, well, if someone has just stuck a bunch of electrodes into a chunk of cortex, these super weird traveling waves, etc., could be happening. But if you're not actually looking for them, how would you find them?
That actually, I have a random question that's inspired by that. If when people close their eyes and it's dark, a lot of times people get these interesting patterns of activity, right? I've never looked at if that is well characterized, but it superficially looks similar to those kind of traveling waves, right? The same sort of period.
Is there something similar with people experiencing migraine where you see a visual pattern before?
That's much, much slower. I mean, the scintillating scotoma in migraine is like, it goes in the middle of visual field and it's scintillating. And then over the period of half an hour, the C shape will go like this, or sometimes it can be like a shape like that. But it's scintillating at a high frequency, and then the frequency that it spreads is like half an hour. So it's suspected to be a I forget there's a 3-letter acronym for the kind of depression that it is, slow spreading depression across the visual cortex for migraine.
I don't know if I can send it.
I've experienced the same thing with a concussion.
I've had those
Concussions can cause
migraines.
migraines. So yeah,
They're weird. They're really weird.
there's great art that shows the art and animation that shows the expanding scintillating scotoma.
It's exactly the way you described it. It's like flickers.
So
I just sent these to you because they will look weird on a big screen. But it's in the chat window. I think you can download them. But basically, every pixel represents the activity of a simple rate model in a distance-dependent network. So it works a little bit like the Conway's game of life, in fact, fun fact, Conway's game of life was born when Conway tried to simplify a network of this sort that John von Neumann had made for neural purposes, more or less. There's all kinds of weird loops in the early history of computers and neural networks because von Neumann was inspired by the McCulloch-Pitts paper. McCulloch-Pitts showed that their neural network was Turing complete. And von Neumann's architecture for the computer was inspired by McCulloch-Pitts. So when you get into debates about whether the brain is a computer or not, there's this entire mess at the start of the age of computer science that makes the whole debate just completely nonsensical.
Yeah, I mean, really the question is the computer a brain? I mean, that's the...
and don't forget, it starts 100 years before with George Boole.
Oh, right, yeah.
Laws of thought.
Laws of thought.
And the laws of thought has nothing to do with Boolean algebra. The modern...
I haven't looked at the book, actually.
It's got nothing to do with like the modern Boolean algebra that we talk about. He wanted to formalize Aristotle.
Oh, wow. I don't know if you guys can see these.
This rotating wave thing is crazy.
Yeah, so these are relatively easy to simulate. I mean, to like set up. But basically, it's a distance-dependent network. So that each neuron is in a 2D grid. It excites nearby neighbors, and it inhibits slightly further away.
Johan,
Yeah.
you said you share these somewhere?
It's in the chat window. You've seen these things before.
I don't see it in the chat window, in my chat window. I don't know if others.
Oh.
Everybody else see it?
Yeah.
I see. They're taking a very long time for me to download though.
They're slow.
Himanshu, I'll send it to you. Don't worry.
Okay, well, I'll just share my screen. They're a little bit lurid color-wise, but and I guess with Zoom, the speed at which it operates, it might not refresh that well. And when I share it, it'll be full screen for you, and probably won't look very good. But can you see that?
Not yet. Yeah, no.
Yeah.
Yeah, we'll probably see skipped frames. We won't see it.
Yeah, it won't be as smooth.
Sorry, Johan, could you, I missed how you described the network. What is the network?
Oh, yeah. So everything is, my computer is a little slow right now. But yeah, so every pixel is a cell that excites nearby neurons with a Gaussian weight for how nearby. And it also inhibits nearby neurons with a flatter and wider. So basically you need the inhibition to prevent just everything from being excited. But if the main sort of fiddliness is tweaking the excitation and inhibition so that you don't get zero activity and you don't get everything active. The twist to make it temporally interesting is that the neuron will self-inhibit. So it's like, well, so it's a little bit like a winner-take-all network with decent winners who say, well, I've been a winner for a while, I'm going to take a break now, and so let somebody else win, which is, how we should structure our competitive systems, right? But yeah, so I just added that to a regular competitive system. So if you don't have the winner taking a break on a slow time scale, then the exact same system is a bump attractor, or I mean, it can work in a bunch of different ways. But if you change the shape of it, you can get like edge detectors and all sorts of relatively straightforward V1 basically inspired stuff. And since we're talking about it, like the psychedelic hallucinations are also modeled with these types of things, and people have been modeling those visuals since the 80s, I think. Some people have worked with who is it, Roger Whittington, Miles Whittington, right? Jason here? He's Jason's here. I think Miles Whittington has done some of this stuff on form factors to do with
Art Ehrmantraut.
Ehrmantraut, right, Ehrmantraut, yeah. Jason, you know him, right?
Yeah.
Yeah. So those are pretty cool, and I think on the right track. They're using similar principles, which is that you just have excitatory and inhibitory kernels, and when you don't introduce this adaptation term, things will stabilize. So you guys are probably familiar with reaction diffusion systems.
Just to tie it back, do you have a dynamic system on this, or is it purely on a network? Do you conceptualize it?
There is no difference between a neural network and a dynamical system, Kale. If it's a bunch of neurons written as dxdt, it is a dynamical system. So whatever is the grid size, 100 by 100 is whatever, 10,000 neuron, 10,000 parameter, 10,000 variable dynamical system is what Johan has there.
Yeah,
I see. That was
not
not
get confused with deep learning neural net type of neural net.
Yeah, it's only 2,500 neurons. The problem with making this, sort of even more pretty is that as you scale up the computation, just takes a really long time. A game of life, on the other hand, it's all extremely local interactions, and all discrete, so you don't have to worry about that. But you won't get like really wild swirly patterns with the game of life. But it's the same principle basically, because that's what John von Neumann was trying to do and what Conway simplified. So yeah, what Karthik said about dynamical systems, I realized that I used to think of dynamical systems in a very narrow way, which is not just differential equations, but actually using the theory of attractors, limit cycles, bifurcations. But after reading this paper, I'm like, well, it looks like anytime somebody uses a differential equation, it's calling it a dynamical system is fair game. But then when you do that, the problem, as is illustrated in all three papers I sent, is that you end up saying trivial things like such and such is a dynamic. I mean, even a stationary object is a dynamical system, right? But yeah. So I prefer to say dynamical systems theory for how I approach the the differential equation.
And Kale, you should not think that dynamical system is a new thing at all. It is very much.
We talked about it, Poincaré and all that.
Not even Poincaré, right? Don't go there. That's like modern topology. Like all of modern math and physics is dynamical system. What are Newton's laws? Newton's first law is basically dynamical system of a body which is in rest. The best example of a stationary body, or as a body which is in motion, which has no force applied. F is equal to ma is the first dynamical system you can think of. If you rewrite d by dt, right? If you change a acceleration as dv by dt or dx square x by dt square, it's again a dynamical system. So the whole, like the entire field of calculus and whatnot you're doing, it is a dynamical system. So all that we're doing is not like some new idea at all. All we're doing is we are extending it to much more harder cases that were not traditionally solved by the classical mechanics and other fields. That's it. It's just an extension.
And I think the most interesting extension is that these are dissipative driven systems. So simultaneously lose energy and gain energy. So only such systems have stability, which is only in the past couple of years did I fully wrap my head around this, because it's a somewhat sort of philosophically interesting thing, right? Which is that the concept of stability requires open systems. A system that is isolated energetically cannot be internally stable. At best, it can be thermodynamically uninteresting, but you can't have any kind of interesting stability in an isolated system.
Sorry, when you say it in that way, what kind of stability do you mean that is impossible?
So
you can't have attractors or limit cycles.
So for example, for example, if you take the two body problem, right, like just the sun and the moon, earth or whatever, the whole equation works because it's a conservative system. It's like energy is conserved in that system. The slightest perturbation of earth in those equations, or the sun in those equations, it no longer is going to follow any of the rules that you thought of. Like it's no longer going to follow that original elliptical orbit or any of that stuff. It might move into a new elliptical orbit.
Yeah, I mean, it's guaranteed to. If the laws are right, then even like an asteroid that passes close enough will change the orbit. Like there's no doubt about it. It might be an imperceptible change, but
given that
will just take the energy.
The dissipativeness is actually the reason why we actually have less collisions and less, more stability in a way. Otherwise, planets should be collapsing on one another all the time. So dissipation and driven systems are the more interesting ones. But the original formulation, it is useful. The conservative Hamiltonian systems get you so far, even with assuming like no friction, etc., no air resistance. You can actually do a lot of work. So it's not like you should throw it away, but for the ones that we are interested in, because they're kind of operating with multiple variables and all that, we have to be more relaxed. So that's why this dissipativeness, open-endedness, non-equilibrium, non-equilibrium, thermodynamics, whatever, in all those regimes, it becomes important.
Yeah. So if you ever look into the Kale, you were about to say something?
Yeah, I was just going to go back to Karthik's point about dynamical systems not being new, but the state space perspective is more new, and examining these things as attractors, repellers, all the phenomena we talked about.
Just Poincaré.
Yeah, that is like Poincaré and those people. But I'm just saying that this is not a Like it didn't suddenly come from Poincaré all of a sudden. It has a long history starting from.
No, I'm more on the side of like Poincaré did something pretty new.
I agree he did new, but I'm just saying that there is a continuation. It didn't come out of nowhere.
So what I was trying to ask about was not is this a dynamical system, but what is the state space perspective or similar that can give insight into these networks of individual things? How can you think of it that way? That's create a diagram.
I do think of it. So working memory, right? The standard model that people use is a bump attractor, and literally an attractor. And so you can ask about the stability of it with respect to perturbations. And so even for rhythmic behavior, you need a limit cycle. For entrainment, you need limit cycle. So in certain specific domains, the modelers are already using the language and are thinking about it, but they typically can't visualize it because it's a high dimensional space. But you can actually use the tools. So for instance, in some situations, you can do the exact same tools that Karthik explained, which is fixed points, linearize eigenvalues. You can do all that. It's just that you may not be able to visualize anything. In fact, people look at the spectrum of eigenvalues of high dimensional systems.
So did you do that with the models that you were talking about?
I didn't. What I was doing was thinking of my system as having an emergent attractor, and then looking at how the attractor would get perturbed and become a limit cycle effectively. It was an unstable oscillation, but
I think that's what I was trying to suggest that maybe you could explain the dynamical systems perspective on the network. That's what I was trying to say, is like how exactly does that work? That might be useful to really go into depth.
So well, it's 10:48, but we can talk a little bit more. Right?
No, another time, certainly.
But yeah, so the concept of invariance, which I'm sure a lot of you are familiar with, lives in an interesting way along with dynamical systems, and it actually relates to maybe what Charlie was saying about comparing things and how they're similar. So just from introspection or just observing behavior, you know that I'm able to recognize dogs regardless of many specifics of dogs, right? So something in my brain says dog, and then I can unleash all the standard behaviors in response to the category of dog. Now, and that's pretty robust, right? So the typical way that people talk about it is like with these, like in deep nets, for instance. It's still a dynamical system, just a boring one, right? But it steps through all these things, and then you can think of the node, the category node at the end of the chain of layers, as an attractor in a way, in the sense that if I perturb the image somewhat, it still looks like a dog. And in fact, they find that it's a very, very strange, not quite attractor, because you've heard of one pixel attacks, right? So what it is it's actually a saddle point in some extremely high dimensional space, where so you could imagine something that is so in such a high dimensional space that if you're looking at it in some subspace, it looks a bit like a valley, but actually it has all these cracks and weird shapes in it that are what allow the one pixel attack. So for us, what we want is something more robust, but also temporally robust, which is not present at all in deep nets, right? Because you train them in batches on their own. It's like somebody who does all their homework, take 10 hours to do an exam or something like that, right? So whereas what we want is a kind of stability that's partly entrained to something in the environment. So you have to, so the attractor language is not just about the fact of an attractor, but the shape and size of it. And like how deep is it? In the case of exploration, you also need to be able to get out of the attractor. So you can think of exploration in terms of like a lot of people just model it as a random walk, right? But actual exploration requires that you pause when to take in things, right? Like you can't just zip around like an actual random walk, right? So that requires that you actually tile your state space as little attractors that give you some sort of, that you're staying there. So for all of us who are in CNS, we implicitly think that way. I have to make an attractor that because the system will not perform well with little bits of noise unless I have an attractor, but it won't be able to explore the state space at all if it's just one gigantic attractor.
So what about instead of just attractors, what if you have attracting trajectories? Because that would at the same time give you both convergence towards the trajectory and sort of an escape from it, because it can be sort of attracting in the beginning of the trajectory and then it can become less stable as you move on through time.
So check this out. I just, right before the meeting started, I asked Karthik about this because I was thinking of, this is sort of an open problem to even frame it properly, which is that you have something that's not a limit cycle and not an attractor that could be doing all kinds of weird things in state space, but which you can reliably get to given initial conditions or input. So I was asking Karthik, if I have like one of those weird gifts that I sent, which is a kind of, it may not actually stabilize. It may just sort of bounce around. I was like, well, if say a system is like moving through such a state, it's a little bit of a brittle system. It'll be a completely different state the next time with similar input. Can I stabilize it? Can I move the system so that it's almost like creating walls around it, right? Can I make a sort of protection of that trajectory where there wasn't much protection earlier? I don't know. And I don't think any of us have an answer, but Karthik has been thinking about related questions for many years.
I mean, isn't that what you want to accomplish with plasticity, with local plasticity?
Yes,
this is just learning, right? I mean,
Yeah. Learning is the way that that is typically used to get there. Have you met Saurabh here? Saurabh and I have been like going on a big trip about like doing it without plasticity. We want to kind of make the adaptive. We want to make it an adaptive system without actually plastic weights. So how do you kind of like crank up or down the strength of feedback? We're calling it the strength of feedback, but it's actually in a feedback activation function. So you kind of like slide away from the feedback function, which is probably in a regime where it's like operating in this, reverberatory mode. We kind of want to like push it away from the reverberatory mode into like sort of like don't do anything to do this, to do that. So it's basically like turning the knob. It's basically like we want an internal system which is kind of doing this bifurcation on its own. Like if you like think about it as a parameter, we kind of want to like the system to adjudge on its own when it should like move from like reverberation to.
So this is what I was working on as a postdoc.
I know.
Like so that I mean, the reason I was doing it is very much along the lines of what Johan was saying before, not to do, which is you have some model of how you think the brain works. How do you force your model to work on the mechanisms? And so I was trying to make art work, adaptive resonance, and so you need to be able to kind of have different states, modes of operation. One in which you're kind of searching for a valley, and you're going to settle and kind of reach stability if there is one. And then other ones, once you've had it, or you're not satisfied with that one, to move to another one. And so that kind of requires like a shift, right? And so, I mean, in that case, it was originally written as an algorithm where you like find it, and then if it's unsatisfactory, you reset, or even if it's a new trial, if you move on to the next stimuli. And actually current neural networks do this, right? Like they're not really a dynamical system because you reset the thing every time you give a new stimulus. So like how does that actually happen behaviorally? How do you like, and I think, this talking about oscillations and stuff like that is certainly relevant, maybe to talking about this, like resetting of synchrony, maybe certainly relevant to that. But I mean, the perspective I was taking was there's some kind of neural modulator that's sensitive to how well, to different things about the situation that could be external or internal or external, that do kind of change this mode of stability. So you go from a more stable kind of regime to a less stable regime that happens like that comes externally, at least to the local circuit, not externally necessarily to the brain or whatever. But
in fact, a simple example of what we're all getting at is with short-term memory, we don't typically use any weight change. So the network doesn't change.
Are you sure about that?
Well, in the model, I don't mean in reality, but I think in the brain, the best way to think about it is all of these things are happening simultaneously. So for the phenomenon that you're interested in, the timescale of the medium and long-term synaptic change may not be relevant to explain it. But enough number of those events will eventually, cause the.
Or you can even think of it this way:
Well,
even if the weights are changing, even if in the short term, memory, the weights are changing, they're still not fully reflected in the network activity for it to actually cause a significant change in the network behavior itself. So during the regime where the weight changes are not all fully complete, you can still assume that the weight changes don't really matter and the system is still operating with whatever activation at the neuronal level. And so that's why I'm talking about, for fast control, we need this kind of automated knob that can move it through the entire
so maybe there's a way to do it with inhibition, but like saying acetylcholine, that's what my thesis was. You can change the level of acetylcholine and you can go from one winner in a network, which is a stable state. It actually stabilizes. And that's, I did with spiking and rate-based models. Sorry to promote my stuff, but I don't do this anymore. But then you change the level of ACH and there is no winner. Everything just does whatever. So that's a knob that changes all the transfer functions of all the cells through.
So SAT is your order parameter.
Yeah.
What is it?
Yeah. I mean, it's a possibility. It's a model that works. I'm just saying it's a model that works and it seems to fit a lot of experimental data.
I've seen plenty of evidence for this. In fact, in the cortex specifically, you even have a kind of push-pull relationship between ACH and 5-HT, serotonin, specifically in layer 5, which actually again ties to that corticothalamic loop. But so you can push the system between having fairly sharp detectors, attractors of something, to having weaker ones, and then being able to sort of bounce among them. So, because the brain has to solve these paradoxical kind of dilemmas, right? Which is, Steve is great at talking about, Steve Grossberg, right? So there's the stability plasticity dilemma. So on the one hand, you want to stabilize useful behaviors and memories, but on the other hand, you need to be plastic enough to change things when they need to be changed. And there are so many different versions of this, like the explore exploit trade-off, right? There's a certain amount of exploration you have to do, otherwise you'll be stuck in some local minimum. But if you keep exploring, then you're sort of extremely suboptimal when it comes to reaping the benefits of all that exploration. And there's no easy solutions. In fact, in the space, in computer science and machine learning and stuff like that, they've kind of shown formally that you cannot come up with perfect solutions to these issues in a problem independent way. Meaning that it's a little bit related to the no free lunch theorem, which is that you have to actually study the specific problem that you're interested in to some for optimization, for instance. And there are no general optimization solutions.
Mm-hmm.
So, shall we
Can
call it an evening? And yes, Charlie,
can I bring one somewhat unrelated point? So Kale brought up the thing about where you close your eyes and you see whatever patterns or anything. Yeah, so I was talking to Jerry Schneider a couple days ago. He's like a retired professor at MIT, and he was telling me that he has this very interesting experience that when he looks at something and he closes his eyes, so often if you look at a bright light, you might get an after image, but he gets something which he calls a visual persistence, where he looks at an object, he closes his eyes and he sees that object very clearly for for let's say a few seconds after that. And in particular, he was saying that he noticed this like at a ballet where he saw a dancer, he closed his eyes, and the visual persistence on the back, sort of the thing that he saw was the ballet dancer kept on moving, kept on dancing. And then he opens his eyes, and obviously his like prediction was a little wrong, and the dancer ended up somewhere else. But for him, it's an extremely vivid phenomena. And apparently he's not the only one. One thing I'm curious about is if anybody else experiences this kind of thing in this group.
When you've been staring at a terminal, if you just close your eyes, you can see a rectangle, and it's actually the color changes. Bright becomes dark, dark becomes bright. Right now, try it. You stare at your terminal and close your eyes. You'll see a rectangular box. I mean, rectangular frame.
And the colors would be flipped, right?
Yes.
Well, the
Yes,
colors
you
flip
get
for him?
a bright screen will show up as a dark rectangle.
Right. So that's an after image. For after images, the colors are flipped. Whereas for what he's describing, the colors are true. And the object that he sees is very clear. And like a test that you can do with this is like take a piece of paper, draw like a smiley face or something, stare at it, like fixate at the center of it for some time, close your eyes, and then see if that image pops up clearly in your mind.
For most people, it's a negative.
How would
It's a
you
negative,
distinguish?
Well, I mean,
how would you distinguish from an after image? I mean, from what he's describing, which seems to be a more imaginative mental construct, especially if it's this motion that's continuing or something like that, from a simple after image. I mean, everybody gets after images, but
right. So
I've
for
not
an
heard of anyone getting the other.
The lack of negativity.
Yeah. So first of all, an after image will not be that precise or clear. It'll be inverted colors. And there's very interesting phenomena with the thing that he experiences. For example, if you take that picture of a face that you drew and you look at it, you fixate, close your eyes, you see that picture. And then what you do is, still with your eyes closed, you just rotate your hand so that now the picture in your hand is horizontal, but your eyes were closed the whole time. You'll see the image rotate in your mind.
Yeah, I mean,
Sounds
I
intense
think
synesthesia.
it's just like really good.
I mean, it's
strong feedback, like what you'd have in a dream, a vivid dream or something.
It's
Exactly.
I mean, like with
no, actually, in meditation class, sometimes they say close your eyes and think of a flower, a rose or something. And some people claim they can see it, but I can't see it.
Yeah, I've heard that in meditation classes too.
Yeah. They say,
I mean,
imagine something, and then people say they can see it.
So Jerry said that roughly like 5 to 10%, maybe closer to 5, I don't know what it is, of people that he like randomly asks experience this thing. And there's some papers on it also. With
Extremely stable, but can they also just conjure up a random image? Like if I say close your eyes and imagine something, are they good at that?
So I'm not sure.
I mean, what you described about like the dancer continuing to move, especially, I mean, I don't know, like it's easy to imagine, it's at least easy for me to like speculate, that after images are kind of leftover inhibition in kind of the ocular system, like that's why it's kind of, inverted, right? It's kind of, and why you see it as kind of like, why it's sort of progressively, because it's sort of like your system does so many weird things with all the edge detection and like emphasizing, and that's where all these neat kind of visual optical illusion kind of things can come from, and so there's lots of ways that you can kind of play with that visually, but it does seem to be like a lot of that is tied up just in the upfront kind of visual processing, whereas something that would involve a dancer continuing to move would be more in kind of high level, what much more complicated sort of event predictive behavior.
Right. So typically people talk about after images as being a retinal based phenomenon, that it's sort of like a burn in your retina. But the thing is, I've had this experience, or that I can do this. I can leave an after image, let's say, do something stupid like stare at a flashlight for some time, then close my eyes, and I can focus on that after image, so to speak, and I can keep that after image there for what seems to be an indefinite amount of time, like upwards of a minute.
I've done this too. It was a long time ago. A strange thing to do.
I've done it recently. You don't even need something that's that bright. You can just stare at
Sure.
something for a while, close your eyes, and pay a lot of attention to the after image. It will last about 60 seconds.
And by focusing on it, you can keep it going longer if you want.
But
So
open question, how do we know where perception takes place?
I think once you've closed your eyes,
True.
Johan, are you
then-
okay? Like, what happened? Like, suddenly you went from like asking some question and you went like, do we know what's wrong with you, man?
No, man, you know what I'm talking about, right?
once you
there are all these, like there are multiple maps. Here's where the philosopher's version of representation does become relevant, right? The multiple maps of the visual system in the neural sense, right? But I only see one thing. So is it possible to localize the actual perception?
Maybe not, right? Like, but because think of it in the clinical way, in the most clinical ways possible, right? What do you need to remove? What shouldn't exist so that your perception still persists? Like, what can be removed? And
that's what Christoph Koch and Francis Crick were doing, right? That's how they found the claustrum or whatever.
Yeah, the claustrum or something, I guess.
The claustrum.
Claustrum.
Yeah. So, but that's kind of not.
That was their quest.
Kind of what they were doing. Like, if you look at like from, it's a much more difficult question to answer, right? Because what part of perception are you talking about as perception itself here? Because you could still perceive something, and then you could have a Gershwin-like system where your two halves of your brain are cut off, but you could still perceive, but you can't act, or you could act, but you can't perceive. So it's sort of like what part of
or you could perceive and act, but not recognize that you have actually done that.
And that. So it's sort of like it's a much more difficult question to answer. Like, so you have to take this clinical perspective and kind of like chop off every bit of the brain, whatever. But how do you do it in humans? So
if there are sensory maps of your sensory motor organs, right? Tie that to the concept of visuospatial sketchpad or the auditory phonological loops. If that is where they are represented, then there is persistence there. That is, when an outside in stimulus comes, you are retaining it. Or if you have a thought which is inside out stimulus, you still bring it to the same place. So you're seeing it in the mapped area in the brain. And it can come from, if it is coming from inside, you are imagining. If it is coming from outside, it is persistence of vision or hearing the external sound.
Which relates to this whole embodied cognition business that
yes.
Some part, but it doesn't actually answer the question of how much of the cortex or which part of the cortex is your projection screen, right? Like, let's say you're internally imagining something.
There's the homunculus concept, right? Project Penfield maps.
But how much? But do I need? Can I manage to do this with just V2? Or like, it's a very hard. And
that's, again, you could. It all depends on, like, you could have persistence in some area without actually having awareness of that persistence.
Precisely. That's why it's
it's not a question that we can even answer in any meaningful.
Correlating the phenomenology with a neural phenomenon is really, really dicey, because there's all these like double dissociations. You can have persistence without the experience. You can have maybe even the experience without the persistence if you haven't looked at the entire brain. Then you might find that, something in the thalamus was firing away. So.
But I think in Charlie's case, I would definitely say that this person has stronger top-down control, for example. The fact that you can hold something without the external stimulus seems to suggest more of that.
To be fair, I'm not sure. Well, why I'm not sure I would call it stronger top-down control is because it's essentially what happens when you dream. You know, you have the
Right.
same sort of generative model that is predicting forward, and then you know you perceive those predictions per se, and you have an experience that's just like your awaking or awake experience. And so you could call it, maybe you would call it stronger top-down control, but it also seems like maybe that same, like we have the same mechanism, just for some reason his is acting up when he's awake in some way.
Yeah, and I imagine there's like different levels or different types of, I guess top down is not quite an accurate word because it requires some, you know, active will involved, and in this case that there may not be. But what you said reminds me of Oliver Sacks' book on like hallucinations. I was just reminded that a lot of people, more people than you imagine, actually experience auditory visual hallucinations, and it's far more common than what people are willing to believe because of stigma associated with experiencing hallucinations. And I think what you're describing just confirms that the brain is capable of a lot more than what we're willing to admit.
Instead of top down, can't you say it's just memory recall and it is coming from inside out, which is the terminology Buzaki uses.
Exactly,
It's inside
like,
out. Thought,
yeah,
it's
maybe.
thought basically,
inside
right?
out. That's a good way. Because
I like
I have a
inside
much
out.
stronger recall of smells than I do of.
Well, I would prefer just call it inside rather than inside out. But
why is it called inside out?
Because it is happening in the knowledge domain, some portions of your brain, and it is coming out, and it becomes motor command, and then your body starts acting. So thoughts are created, thoughts are recalled memories coming out of the cortex, and they become motor commands. And if it is a physical action, you express it through your body. And if you're going to make it a verbal speech, you issue the commands to your vocal cords. And so the inside out is inside out is a fancier word for action. Outside in is the fancy word for sensation.
But then hallucinations are not necessarily actions, right?
It is action. You are creating. Action doesn't have to be musculoskeletal. Moving some, creating neuronal assemblies is an action. You're pumping energy.
In the same sense that the outside world is acting on our brains, right, and creating neural assemblies as well. Yeah, it's a similar concept. Then
this is the dorsal stream and the ventral stream, right? One is coming from inside out, the other one is going from outside in. And if the inside out is influencing, you call it control. Otherwise, it is just communication, going two parallel streams communicating in opposite directions.
And ultimately, if you include time into it, the inside is the outside from earlier, right?
So I like to think about it from like Andre Bastos' perspective of like the top-down predictive coding, actually.
Jason,
you have like frontal to posterior, cortical.
No.
No.
Let's not talk about Andres Bastos.
Stop the recording now.
Jason.
Stop recording.
Stop recording. I broke.